Yeah, thank you so much. And first of all, yeah, thank you for inviting me. It's amazing to be here in this nice place, and also it's nice to talk about things that are very close to my heart. Um, yeah. So today I wanted to talk about a line of research at the intersection of two fields that look like completely unrelated: algebraic geometry and deep learning. And yeah, let me start from the obvious. Yeah, I mean, machine learning, deep learning especially, is everywhere, right? But still, we kind of don't understand it well. So not only we don't understand, at least from mathematical perspective, we don't really understand how neural networks work, but actually, we don't even really know what type of mathematics we should use to understand deep learning. And to give an overview, here is a partial list of fields of, if you wish, mathematics that have been applied or that have been leveraged upon to understand different aspects of deep learning. I mean, we go from probability and information theory, classical learning theory, to Riemannian geometry in the form of information geometry, to statistical mechanics, which many of you work on, to geometric deep learning. But yeah, but the point is that today, so the moral here is that there is all kinds of mathematics, all kinds of fields in the vast landscape of mathematics that have been explored in the context of deep learning. But the big missing field, in my opinion, is algebraic geometry, which is a shame because algebraic geometry is a very popular field in pure mathematics. It's maybe the most popular field in pure mathematics, I would say, at least in the culture I come from. And it's quite a shame that it has not been considered in the vast field of machine learning. So today I'm going to try to fix that. But first of all, let me explain you what is algebraic geometry, because maybe you've never heard of it. So from the most boring perspective, algebraic geometry is the study of, it's a type of geometry, it's a study of some type of spaces. And in particular, it's the study of spaces defined by polynomial equations. That's the most basic definition of algebraic geometry, is the study of spaces of solutions of systems of polynomial equations. So kind of generalization of linear algebra to the non-linear setting. This sounds quite special, but actually I would like to reflect on the fact that polynomials strike an amazing balance. First of all, they are general. If a system of polynomial equations sounds like restrictive to you, think of the fact that any continuous function, at least locally, can be approximated by polynomials. So actually, this type of spaces capture essentially any kind of space you can think of, essentially, up to an approximation. But the fact that they are defined by polynomial equations makes all of this very tractable. That's where the word algebraic comes from. So polynomials are very explicit mathematical objects that on which you can do explicit computations. And so algebraic geometry leverages on this sweet spot between being tractable and being general. And this has led to a very rich field of geometry. So just to name a few things that algebraic geometry has given us, I mean, it has given us, of course, some type of cryptography. Elliptic curves are the most famous curves in algebraic curves. It has given us string theory, which is the field where these kind of spaces appear, also very well-studied algebraic varieties. And also it has given us number theory. For example, Fermat's theorem is maybe the most famous result of contemporary algebraic geometry. And funny enough, in this talk, the Fermat's theorem will come back. So stay tuned. It's very fun. There is a very fun connection between Fermat's theorem and deep learning. But yeah, so algebraic geometry has given a lot to pure mathematics and related fields. And so today we ask the question, how can we leverage all this richness, all this stuff that has been developed within mathematics to understand the mysteries of deep learning? So this is really what I would like to talk about today. And so, yeah, let me try to answer this. Let me try to look for something in this intersection between algebraic geometry and deep learning. So if I want to do algebraic geometry or any kind of geometry, the first thing I need to give you is a space. So I need to focus on some particular space that appears in the context of machine learning. And this space is the following one. First of all, let me define what is a machine learning model for me. In the most vague or general concept of a machine learning model is just a parameterized class of functions. So it's something that, given a parameter space, input space, and output space, for me, a machine learning model is a map from parameter space to function space. So it's a parameterized class of functions. And I call phi the parametrization, so the map that, given the parameter, associates with the function in the function space y to the x. And so the space I'm going to focus on today is the neuromanifold, which is defined simply as the image of the parametrization. So the neuromanifold is the set or the space of functions parameterized by your machine learning model. It's also called hypothesis space in statistical learning, but I'm going to call it neuromanifold, which is a term from information geometry to highlight the fact that I'm going to focus on the geometric aspect of this space. And yeah, in pictures, again, you can take any machine learning model, a deep neural network. Each parameter defines a function, but when you vary the parameters, you span a non-trivial, curved, weird space of functions. So the neuromanifold is this red curve, and this space lives a priori in an infinite dimensional function space. So that's the setting. Okay, and how do I learn from the perspective of the neuromanifold? Let me give you my view of what learning is. In one slide, I think of machine learning in the following way. I have some data, but the main point here is that the data comes from a ground truth function f star. So f star is this platonic object that I don't have access to, but data comes from it. And then, for me, learning is a statistical approximation of a distance minimization problem, in the sense that what I want to do is find the point on my neuromanifold, so the function parameterized by my model, which is closest to the ground truth function. Again, it is a statistical approximation in the sense that I only have access to data, so it's a falsification of this kind of geometric problem. But ideally, so the ideal learning problem for me is a distance minimization problem over the neuromanifold, which is a purely geometric problem, and that, at least in some contexts, can be studied as this, in this abstraction. Okay, but we want to do algebraic geometry. So now I'm going to assume that the given machine learning model is polynomial in both the input and the parameters. For example, the two main examples of this setting are deep neural networks with a polynomial activation function. So if the activation function is any polynomial, then the whole network from input to output is a polynomial, both in the input and the parameters. But also a bit of a more modern example is linear attention mechanism. If you take an attention mechanism and remove the softmax, so this is what linear means, you get a model which is algebraic. It is not actually linear. It is a cubical because of key, curious, and values. But it is a polynomial. So if you stack linear attention layers with fully MLPs with a polynomial activation function, you get an algebraic model. So kind of an algebraic transformer. And again, polynomials can approximate anything. So if you're not satisfied with this, one way I can convince you is that if your network does not have a polynomial activation function, just approximate that activation function with a polynomial. Up to a small, arbitrarily small error, it's going to be the same model, essentially. But now you have replaced your non-algebraic model with an algebraic model to which all of this applies. And so what are now the two immediate advantages of an algebraic model? First of all, something that sounds innocent, but it's actually extremely important. We said that a priori, the neuromanifold is a finite dimensional space, nonlinear space, but that lives in an ambient dimensional infinite space, the space of functions. However, for algebraic models, you can actually take the ambient space as being finite dimensional. I mean, if your model is a polynomial, then your neuromanifold, so all your functions are contained in, for example, the space of all polynomials of a bounded degree. And that's a finite dimensional linear space. So neuromanifolds of algebraic models actually live in a finite dimensional ambient space. And by the way, this is not true for non-polynomial models. So as soon as your activation function is not a polynomial, there is this negative theorem kind of. It's not true. The vector space spanned by your neuromanifold is infinite dimensional. So this is actually peculiar of algebraic models.
Giovanni, maybe you could comment on it, but by this restriction, you are actually going away from the space of activations for which the universal approximation theory is.
That's a very good point. So
and how is that not a big
problem? So there is this question, does universal approximation theorem hold for polynomials? I mean, the answer is actually yes, in the sense that...
Not for bounded degree, right?
Well, depends. So depends what you mean by universal approximation. Of course, the classical universal approximation by Seebenko and Hornig does not hold for polynomials, right? Because of this, actually. If your neuromanifold is contained in a finite dimensional space, and that space depends only on the degree, then you cannot approximate everything, because a finite dimensional space cannot be dense in an infinite dimensional space. However, if you vary the depth instead of the width, so the classical approximation theorem is fixed depth, arbitrary width. And if instead you do the other way around, fixed width, sorry, I'm getting confused, but non-fixed depth, then polynomials are universal approximators. So this is the contemporary approximation theorem. It's a paper from Colt in 2000. It's actually quite recent, this thing. So the theorem is that any activation function which is non-linear, of course linear doesn't work, with fixed depth, but with fixed width, but arbitrary depth, you approximate everything.
So even quadratic, even if I stick to quadratic,
and I actually
large depth.
I actually sat down and wrote an explicit proof for the quadratic network. It's actually very fun with algebra. Because I was also surprised, I was like, wow, quadratic network, if I, with fixed width and arbitrary, I sat down and wrote explicitly how to write an arbitrary polynomial as a deep quadratic network. It's very fun, actually, exercise.
And does the depth need to be large in the same sense as the width needs to be large for the...
I mean, how large? I thought about... I don't remember. I mean, of course, it should be large in what, though?
The dimension.
Well, I think it should be large in something like the Lipschitz constant of the function you're trying to approximate. And how large? Probably logarithmic, because it's that. But I'm not. It's in the Colt paper that proves this. Estimates, I can't say it in the top of my head. But yeah, it needs to be quite deep, just as in the classical theorem, networks need to be quite wide to approximate. But that's a very good point. So of course, this fact that sounds innocent, it's good from geometric perspective, because now I work in finite dimensional geometry, but from universal approximation, it immediately tells you that you cannot universally approximate by varying width, but by varying depth you can. And now the main thing, I mean, I've told you that algebraic geometry is the study of spaces defined by polynomial equations. Well, I mean, you can guess that if my model is algebraic, then the neuromanifold is an algebraic variety. So it can be defined by polynomial equations. This is actually completely non-trivial. It's a very famous theorem. This is actually a theorem in logic, fun, Tarski is maybe biggest logician of the 20th century. And it's a theorem in pure logic, but you can translate it in the algebraic context to prove that the neuromanifold of an algebraic model is an algebraic variety. But of course, it's very intuitive. You have polynomials in the definition, you get polynomials in the neuromanifold. Okay, so how can those neuromanifolds look? So I'm going to immediately throw at you a rendering of a real neuromanifold. So this is an actual rendering that we did. Here I'm showing you what is this. So this is, well, it is a 3D slice. So this is supposed to be a high-dimensional object in a high-dimensional space, but this is a 3D slice. So the intrinsic dimension of the slice is 2, is that surface, but it's a 3D slice of the neuromanifold of a linear attention mechanism. And you see, it's quite weird. I don't know, it looks more like a Calabi-Yau manifold right from before. It's very weird. It has some self-intersections. It has this very weird line that comes out and comes back in. We will get back to this line. It's very special. You can interpret it from machine learning perspective, but they look like, so even one layer of a transformer looks like this. So the spaces, I would say, are quite non-trivial. They can have weird singularities, self-intersections, extremely curved. So they can be quite non-trivial, even in very simple examples like one layer of linear attention. This space, we understand it quite well mathematically for one layer of attention, but it looks like this, but we can't understand it. But now let me go from the complicated example to the simplest example I can think of, so the other extreme. Let me take the simplest model that I can think of that I'm brave enough to call deep network or network, you know. I'm gonna consider a two-layer biasless linear network. So 2 layers, no activation function, but it's also gonna have a bottleneck. So it's gonna have n inputs, m hidden units, and then also n outputs for simplicity. So like a bottleneck. And so this network just takes the input and multiplies it by 2 matrices, the first and the second layer. What's the neuromanifold? I mean, the answer is quite clear. The neuromanifold is the space of linear maps, so n times n matrices, of rank at most n, just because there is the bottleneck. Okay, so, but this space is also very studied in algebraic geometry. It's called the determinantal variety. I mean, just to show that it is an algebraic variety, we need to look for polynomial equations defining it. But now the space of rank at most m matrices can be defined by the simultaneous vanishing of all the m+1 minors. So a matrix has rank m if in only if all the m+1 minors vanish. The minors are determinants of submatrices, so they're algebraic. The determinant is algebraic in the matrix entries. It's a polynomial. And so this is a system of polynomial equations whose space of solution is exactly the determinantal variety. So this is another example of an algebraic neuromanifold. And again, this model sounds very innocent, but this space is actually not trivial at all. We will get also back to it later on. You know, you can try to think of it. Space of all matrices of rank at most n. What do I know about this space? Can I tell something about, I don't know, self-intersections, curvature? It's actually a quite non-trivial space already. Of course, it's very well understood in algebraic geometry, but you know, even an innocent model can give interesting neuromanifolds. Okay, and so we refer to the study of algebraic neuromanifolds, so of neuromanifolds of algebraic models via algebraic geometry as neuroalgebraic geometry. So this is a recent position paper that we wrote, where we baptized this kind of field as neuroalgebraic geometry. So I don't know, that's the name, kind of the official name of all this line of research. And we even have a logo for it. So this is the logo of neuroalgebraic geometry. Maybe it doesn't tell you much, but this thing is a very famous doodle in mathematics. It was drawn by maybe the most famous mathematician in history. When he proved his best theorem, he drew this thing. And here there's supposed to be the theorem, but I photoshopped it and put a neural network in it. So now this is the logo of neuroalgebraic geometry. This, by the way, it's probably my favorite theorem ever. I mean, it's, yeah. Okay, and so in the second part of the talk, what I will try to do, so now, okay, fine, we can study neuromanifolds of algebraic models via algebraic geometry. What does this give us? What do I add to the deep learning literature or to the deep learning or machine learning landscape? So in the second part, I'm going to discuss more in detail what from algebraic geometry we can borrow and apply to machine learning, and what results it has given us, to the community in the past years, and what is the research plan more long-term. Yeah, so to begin with, so here I have a dictionary between some problems or questions in deep learning and some related objects or ideas or tools in algebraic geometry. I'm not going to go through this table because in the remainder of the talk, I'm going to go through every single point here and explain it in detail. So this, if you want, is a table of contents for the remaining part of the talk. Okay, let's begin with dimension and degree. So in algebraic geometry, one thing we like, I mean, that's kind of in the word algebraic, is to describe spaces via numbers. So that's algebra. So this is something that comes from algebraic topology. We kind of borrowed it from algebraic topology. So we want to describe a space by numbers, some numbers that quantify some aspects of the space. And those numbers, surprisingly, are often integers. The most famous one is dimension. I mean, dimension in any field of geometry is, in some sense, the number of intrinsic degrees of freedom of your space. So it's a measure of capacity. Okay, of course, it's also defined in algebraic geometry, but way more interesting is the degree. Okay, so this is a very special algebraic geometry. So you don't have it anywhere else in fields of geometry. Of course, it's related to the degree of a polynomial. If you think of it, what is the degree of a polynomial? Well, it's the number of bends that the polynomial makes. So indeed, the degree of a variety of an algebraic space is, in some sense, the number of twists, of bends of this space in its ambient space. And so it's a measure of curvature. It's actually very much related to curvature. That theorem from before with the devils, that famous theorem, relates the degree to the curvature. It's very intuitive. The degree is number of bends, but it is related to the Riemannian notion of curvature. But it is a natural number. You know, it's like it's a three bends or 4 bends actually. Okay. Okay. Why is it interesting in machine learning? I'm going to just throw at you the fundamental theorem in this line of thought. So dimension and degree are related to sample complexity of your model. So the sample complexity in the classical sense, in the classical statistical learning theory sense, in the PAC sense of an algebraic model. So the PAC sample complexity of empirical risk minimization is linear in the dimension and logarithmic in the degree of the neuromanifold. I mean, of course, this reminds you of the fundamental theorem of statistical learning. So the fundamental theorem of statistical learning tells you that the sample complexity of a binary classifier is linear in the VC dimension of the neuromanifold or hypothesis space, if you call it. However, so here you also get linear in the dimension. So of course, the notion of dimension is different. VC dimension is a combinatorial version of dimension for binary classifiers. In the continuous geometry, we can just use usual dimension. There is no need for VC. However, here the degree appears. So it's very peculiar. In the continuous case, when your neuromanifold is a continuous object, so not for binary classifiers, but continuous, it not only matters how big is your manifold, your hypothesis space, your neuromanifold, but also matters how curved it is. So the degree matters. If you don't have an algebraic model, you don't get a clean theorem like this. So as far as I know, the cleanest fundamental theorem of learning for continuous, like neural networks, is this.
But can you clarify in the sense of PAC learning what that means? Because you mean this is like statistically how many samples are?
Yeah, exactly.
That's not computational.
Not computational. Not computational. This is
kind of a caveat.
It's a caveat.
Because otherwise, like I mean, if there was not for the computational complexity issues, then learning theory would probably be easy. It would probably already exist, and we would not be saying that deep learning is a black box. And all.
I agree. So this is non-computational, like classical PAC learning, right? Like the classical version. I agree. The caveat is that this is non-computational. Like it's just sample complexity of ERM, where ERM is an oracle minimizer. Like just like the classical fundamental theory of study. Of course, you can try to carve out, just like in the classical case, computational versions of that. And you probably get a trade-off, of course. Then, yeah, of course. But this is just to begin with the most classical fundamental theorem of statistical learning for algebraic things. If you don't have an algebraic model, I want to stress out, you don't get something that clean because you don't have a notion of degree. And then here there are versions of that, of course, and it's a big field, but they're not that clean. This is, I think, the cleanest fundamental theorem of learning that I've seen in the continuous setting. And it's actually quite recent. It's a paper by Khalil. Khalil is a big person in this line of research, Joe Khalil. And okay, so first advantage of algebraic geometry, we have a new invariant, a new discrete invariant, the degree that's related to curvature, that gives us a clean version of the fundamental theorem of statistical learning that gives us a clean bound on sample complexity. And it's also nice what it implies. It implies that not only the capacity of your neuromanifold matters, but also how it's curved. Right? So the more curved your neuromanifold is, the harder, at least from PAC perspective, it is, the more samples you need to learn, the harder it is from sample complexity perspective. Okay, so this is the statistical learning part of it. Let's move on to identifiability, the second thing I would like to talk about. So identifiability is a traditional problem in deep learning. In actually beyond, it's in machine learning system identification. It's a traditional problem in, let me say, applied sciences. So in machine learning, what does identifiability means? Well, the problem asks for describing all the parameters that define the same function. Okay, so in more mathematically, given a function, so a point in your manifold, we want to look at the fiber. So all the parameters that map to the same function, to that fixed function. It's called the fiber of f, the fiber of the parametrization based at f. And now another big thing of algebraic geometry is that fibers of polynomial maps are very well behaved. I mean, there are many instances of this general principle, but the point is that for almost all the fibers, we call this the generic fiber. So generic fiber means almost all the fibers. So for almost all f, the fibers share a lot of properties. Okay. So, I mean, you can think of, I mean, an instance of this is over the complex numbers, a polynomial of degree, almost all polynomials of degree n have n distinct roots, almost all of them. There are some special ones, but almost all polynomials of degree n have n distinct roots. So it's this type of behavior. So almost all is ubiquitous in algebraic geometry. This generic, the word generic is everywhere in algebraic geometry. Okay, what's the advantage of this? So if we understand the fiber, and in particular the generic fiber, we understand two things. First of all, we can compute the dimension of the neuromanifold. So the dimension of the neuromanifold, I mean, it's a general theorem, but I'm translating it, is the codimension of the generic fiber, which makes sense. I mean, what is the intrinsic dimension of your object is the number of parameters minus the degree of redundancy. The point is that the degree of redundancy, so the dimension of the fiber, is constant for almost all fibers, and that doesn't happen in differential geometry. So this, and the other thing, so these fibers are also called parameter symmetries. Maybe today, maybe there are these surveys in deep learning where they switch the terminology from identifiability to parameter symmetries. And there is this principle that if you understand the parameter symmetries, you understand the input symmetries. So if you want, there is a duality, an adjunction between parameters and inputs. So if you understand the symmetries in parameters, you kind of can say something about input symmetries. And of course, input symmetries are, you know, are the main topic of geometric deep learning. So networks that have symmetry properties behave well with respect to symmetries from input to output. And I mean, I don't have time to go into this, but essentially one result here is that by using this, so by reducing the problem of studying invariant neural networks, by reducing this problem to a problem of identifiability, we have this paper where we prove or kind of give a mathematical argument to why Fourier features emerge in invariant models. And the main point of the argument is we want to understand invariant neural networks, so input symmetries, but we reduce the problem to an identifiability problem, which is much more tractable and you can actually prove things. So that's identifiability. And since it's such a big topic, I wanted to tell you what is the state of the art of identifiability. So this is a good excuse to give you a bit of literature in this line of research. What actual results have been proven? Okay, so if you take an MLP, let's say with a polynomial activation function, what do you expect to be the parameter symmetries of that? Well, definitely you can permute neurons in every layer, for sure. And also you can rescale the incoming and outgoing weights of a neuron, but this works only if the, did I write it? Only if the activation is homogeneous. If the activation has no homogeneity property, that doesn't work. But definitely you always have permutations and depending on activation, rescalings. If that's true, this was a huge conjecture. So even for monomial activation, so if your activation is a power, x to the r, but with r large enough, of course, it doesn't work for small r. For r equal 1, you get a linear network. But if r is large enough, this was a big conjecture, again, Khalil. So this is kind of the paper that started this whole line of thought, and has been recently proven via the Fermat's theorem. So this is funny enough. I know it sounds crazy, Fermat's theorem in deep learning, but I mean, so it's, to be fair, it's the Fermat's theorem for polynomials. So instead of numbers, you have polynomials. And you can kind of guess how the Fermat's theorem is related. I mean, Fermat's theorem is about powers and sums of powers. And I mean, a neural network with a power activation function, you know, layers do linear combinations of powers. So kind of Fermat type of territory. And that's the proof, kind of. They proved this identifiability conjecture via a form of the Fermat's theorem for polynomials. So yeah, funny enough, who would have expected Fermat's theorem, something you hear, you know, I don't know, you know, in magazines, right? That you actually solve identifiability conjecture. Okay, then we went on very recently. Like, yes, we went on very recently. We said, okay, fine, can we refine this proof? And super recently, we managed to prove the same thing for almost all polynomials. Again, this almost all comes back. So for almost all activation function, polynomial activation functions, you can prove that the generic fibers, so the generic symmetries of the parametrization are only permutations. Okay, so for convolutional networks, you cannot have permutations because the weights are tied, so are shared, so permutations are no longer a symmetry. So we prove indeed that up to rescalings, the parametrization is one-to-one almost everywhere. So this is for single channel CNNs. Of course, if you have multiple channels, you again can permute channels. But for a single channel, the parametrization is one-to-one, again, almost everywhere. These type of maps that are one-to-one almost everywhere are super studied in algebraic geometry. They are called birational maps and are objects of study of the field of birational geometry, which was invented in Rome by Cremona. So this is really where I come from. So birational geometry is really, at least traditionally, an Italian thing. And for attention networks, well, I don't have time to go through it, but I've told you that linear attention is algebraic, so let's take an opportunity. Can we prove identifiability for linear attention? I mean, we have a paper on that recent, kinda, in the sense that if you take only attention layers, linear attention, and a single head, so that's the caveat, a single head, you can prove complete identifiability. So you can characterize all the symmetries. Of course, the symmetries then are different in the sense that, you know, you can transform keys, you can transform queries, but you can cook up a similar story for attention-based networks, linear attention-based networks, so completely algebraic. Okay, and the last thing I wanted to talk about is my favorite thing in all these stories. So if now you're not convinced, maybe you don't care about statistical learning. I mean, so I'm not a statistical learning person. If you don't care about identifiability, symmetries, geometric deep learning, let me take a last chance to convince you why is this story interesting. One last thing, and that's going to be singularities. So algebraic geometry is a very special field of geometry in the sense that it can deal with singular spaces. No other field of geometry that I'm aware of, at least traditional, can deal with singularities. So what are singularities? Well, I'm not defining them, but they are special points. You can think of self-intersections, cusps, edges, nodes, all that weird points where geometry is degenerate. Those are singularities of varieties of spaces. Okay, and so why are singularities of neuromanifolds interesting in machine learning? Because I'm gonna argue a bit that singularities bias the learning process in some way, in some sense. So I'm claiming that singularities are a form of a geometric bias for learning. Let me give you a first idea of why this is true. Again, I'm thinking of an ideal learning problem. So I'm thinking of just distance optimization. That's all I'm thinking about at this level. I'm thinking that learning is optimizing a distance on my neuromanifold from an external Platonic ground truth function. And to study this, I don't know, the best way I see is to consider Voronoi cells. So the Voronoi cells, I mean, I have the definition there, but basically in the context of neuromanifolds, it means the Voronoi cell of a point in the neuromanifold, let's take this small blue point, is the set of all ambient points, so of all ground truth functions, such that this point solves the distance minimization problem. Okay, so if I take this point, which is a smooth point, it's not a singularity, the Voronoi cell is going to be contained in the orthogonal line, orthogonal to the neuromanifold passing through that point. But if I take a singular point, so this cusp, the Voronoi cell is this whole cone. So the moral is that the Voronoi cells are, it's not always true, but for many types of singularities, Voronoi cells of singular points are larger, even in dimension, one-dimensional object, two-dimensional object, than Voronoi cells at smooth points. This means that if I take a point in my neuromanifold and I ask the question, for how many or what measure of ground truth function, for what ground truth functions, will that point be the global minimum of the distance minimization problem? The answer is zero measure for smooth points, so few, a lot, like full measure for singular points, so a lot. So this, for me, my view, I don't know, this is a version of a geometric bias. Like I'm saying that if I take a fixed, if I choose my favorite point, my favorite function of my neuromanifold, and I ask the question, how many times, in some sense, will I end up there with a global oracle minimizer where, where we are thinking of distance minimization? The answer is almost never for smooth points, but a lot of times for singular points, if my points were similar.
So just a question, this is with respect to the choice of the input. Like when you say of.
No, with respect to the choice of the ground truth function.
Of the ground truth function.
So if you want of the data, but I'm not brave enough to call it data. I'm thinking here, there is no data, I'm thinking here of the ideal learning problem where I'm optimizing the distance of my neuromanifold from an ambient function. So with respect to the choice of the ground truth function, there is a full measure of ground truth functions such that the global minimum is this, and there is a zero measure of ground truth functions such that the global minimum is this.
Okay, but morally also the data.
That's the thing.
That's what you would
exactly
say.
Exactly, but I'm not yet good enough to prove this is in the actual statistical context. Okay. So this is all I can do up to date. So this is for the Platonic ideal learning problem when I have the ground truth. But of course, I would phrase it. I mean, the conjecture I would have would have a statistical learning flavor. That this is true if with respect to sampling the data. But of course, then we are in statistics, in geometric statistics. So it's okay. Okay. Okay, and okay, singular points are interesting from a machine learning perspective, but okay, but now, what do singular points of neuromanifolds of neural networks correspond to? Right now that we've learned that in general, singular points are interesting on a neural manifold, but now let's take an actual neural network and let's ask the question, what points are singular? This has a clean answer. It's a theorem conjecture, again, in this recent preprint we have, it was quite rushed, so the theorem conjecture is proven for some models and partially, but unproven for others. But I really believe in this. Singular points of neuromanifolds of algebraic models correspond to subnetworks. Subnetwork meaning that some neurons in your network, whatever neuron means for attention mechanisms, some neurons in your network are dead, in the sense they do not participate in the forward path. This happens, for example, when the incoming and outgoing weights to your neuron are zero. So you can just remove the neuron and you get the same forward path, the same function. Okay, so this is kind of proven with some actually strong assumptions, but let's call it conjecture. Okay, and this is the picture. I have my neuromanifold. I have this point. What are the weights, like the parameters corresponding to this point? Well, there are some neurons that are dead. So these weights, the light blue weights are zero, but I'm allowed to vary the other weights. I mean, in this case, okay, the picture is bad. I mean, in this case, it's just one point, right? So there is no degree of freedom, but Okay, it's an ideal picture. So singular points correspond to subnetworks. And now if you put together what I said before, that singularities define a bias for learning, and the fact that singularities correspond to subnetworks, you obtain kinda a mathematical geometric picture of the sparsity bias, of why, at least in some contexts, we see neural networks converging. It's not always true, but why it's indeed the Voronoi cells. I mean, it's not always true that you end up in that Voronoi cell, but it's often true that you end up with a sparse network at the end of training. Put these things together. Subnetworks, so sparse, if you want weights, correspond to singular points, and singular points bias the learning process, so often solve the ideal learning problem. Okay, I think I owe you a bit of a break, and let me get back to the simplest example, so to the determinantal variety. So let's get back to linear network, 2 layers with a bottleneck, and let me go through everything that I said in this particular example. The generic fiber is GLM, because in a linear network, I can transform the first layer and transform the second back by an arbitrary linear transformation, and that's all I can do generically. The general linear group, in the space of invertible matrices. So the generic fiber is the same as invertible matrices. The matrix transforms the first layer and transforms the second back. So the dimension of the neuromanifold, so this is essentially, if you want to relate it to sample complexity of low rank matrix approximation, so learning on this neuromanifold, is the number of parameters, so 2 matrices n times n, minus the dimension of the generic fiber, m squared. The dimension of this thing is m squared. Okay, and most importantly, maybe the singularities of this space, we understand them very well, correspond to matrices of even lower rank. So a random matrix of rank at most m will have rank exactly m. But the matrices that have strictly lower rank are the singular points. And those are the same as smaller networks, subnetworks, because if a matrix has smaller rank than my bottleneck, I can represent it by removing neurons. So we see the connection with subnetworks very cleanly in this case. Okay. Okay. Okay, and now I'm gonna try to tell an even more compelling story about the singularities. So I will say it in advance. What I'm gonna say here is very far-fetched. It is the object of it is the content of a first paper that we wrote this year. It was a big collaboration, but let me tell you how I envision more deeply the role of singularities. Okay, it is related to the sparsity bias, but I think it is related to much more. So first, subnetworks define a combinatorial structure over the neuromanifold. I mean, subnetworks can be included in each other. I can add a neuron to a subnetwork and remove a neuron. So the subnetwork topologies define a combinatorial structure in the sense that I have my neuromanifold, I have a subspace corresponding to subnetworks with a given topology. It is included in the subspace of subnetworks with a bigger topology, and so on. This type of structures is called stratifications, like stratificational, I don't know, in geometry and topology. So subnetworks define a stratification. And here I claim that this stratification is related to feature learning. So to how neural networks might learn features, at least in some contexts, at least. Why? Okay, so first of all, this story holds only when we start very close to the origin. So if you assume that you initialize your network super close to the origin, the story is kind of precise, at least in some cases, when the initialization at the limit of vanishing initialization, so when the initialization really goes to 0. But assume you start near the origin. The origin is the most singular point. All neurons are dead. No neuron participates in the forward pass. Okay? What happens during training? During training, the model transitions between the singular strata, subnetworks, gradually desingularizing. So it means that all neurons start as dead, inactive. I claim that during training, one by one, the neurons activate, and meaning that their weights transition from being close to 0 to being away from 0. In other words, my function jumps between the singular strata of the neuromanifold. My active subnetwork becomes bigger and bigger. So transition occurs when and so this transition, so a neuron becoming active, so transitioning from being dead to active, I interpret it as being an event of feature learning. So we might think that that neuron, whatever that means, has learned a feature. Again, its weights enlarge, so this neuron joins the active subnetwork, and over the neuromanifold, we are jumping between the singular strata. And from the point of view of the loss, at least the training loss, this corresponds to a sudden drop. Okay, maybe this is confusing. And again, so I'm going to refer to this work. This work is not phrased in the language of algebraic geometry, but it proves this kind of stuff, at least for some simple models. And some people in this room, I think, kind of worked on this for some models. But instead of trying to convince you more about the story, I'm going to just show you a picture that summarizes all of this. So this is, again, how I think learning. This cube is my neuromanifold. The singular strata, I mean, I have very singular points, vertices. I have slightly less singular points, edges, faces, and so on. So those are the strata of my neuromanifold. Again, the most singular point corresponds to the empty subnetworks. All weights are 0. Edges correspond to weights where one neuron is non-zero and all the others are 0, and so on and so on. So according to me, learning starts near 0, so the most singular point. And as the initialization becomes smaller and smaller, so this is really true when the initialization is 0, it jumps. So it starts near the origin, so all neurons are dead, loss is high, so this is the training loss. Then it stays kind of constant, and at some point it suddenly jumps. When the loss jumps, this corresponds to some neuron activating, and from the point of view of the neuromanifold, you are jumping to an edge. And so on and so on. So one neuron activated, I jump to an edge. A second neuron activates, and I jump to a face. And so on. I mean, in this case, for this small network, it ends like this, but in general, it continues until I converge. So this is the image I have in my head about feature learning, at least at the vanishing initialization scale, and how it is related to the singularity theory of the neuromanifold. So the moral is that the singular structure of the neuromanifold guides learning, at least in this regime of vanishing initialization, and kind of gives a geometric perspective of the sudden drops in the loss.
And here, like, how much you have in mind the algorithm? Because for instance, you mentioned, is this only for gradient flow, or is it for a bigger class of algorithms?
I think it's
paper title, you mentioned alternating gradient flows.
But alternating is what we introduce there. But so the algorithm there is gradient flow. I think it's very peculiar to gradient flow, yeah. So alternating gradient flow is what we introduce in that paper, where we summarize this process as a bi-level optimization process. I mean, I don't know if I should go into that, but all this jumping thing of transitioning from subnetwork to subnetwork, this is what we call alternating gradient flow. But the learning algorithm here is gradient flow, and so.
Okay, because in say computer science, I would understand alternating gradient flow as some kind of version of gradient flow where I fix everything and do gradient flow with respect to something and alternate.
It's bi-level, yeah, but this is exactly what it is. But this is something that we introduce to as a limiting process at vanishing initialization of the actual gradient flow. So I would not focus on that because this is something introduced in the paper. It's not something from the literature. But the algorithm here is gradient flow. Yeah. Maybe stochastic gradient flow, in the sense that for us it's just gradient flow, but the initialization is stochastic. Like we really need a stochastic initialization, but whose variance goes to 0. So there is stochasticity, at least in the initialization. So it's actually, it's a degree 1, like it is technically a stochastic process, but the stochasticity comes only from initialization. So the PD you get is degree 1 PD. Like the Fokker-Planck equation is degree 1, so there's not much stochasticity. Okay, I'm already over time, so I'm good. Yeah, and of course, I mean, if you want a mental picture for this, you can think of the simplex algorithm from linear programming. That does a very similar thing. You optimize over a polytope. A polytope for me is a very simple example of an algebraic variety with singularities, and you jump between the strata, between the faces of varying dimension. So I really think that at least advanced initialization, feature learning is really about something akin to the simplex algorithm over the singular strata of the neural manifold. Okay, and so to conclude, let me, so today we have seen neuroalgebraic geometry, this term that we made up to encompass a line of research that bridges algebraic geometry and deep learning. And I want to leave you with two fundamental questions. So what are two really fundamental things that we in the community would like to see in this line of research? One thing is a unifying theory. So maybe you got the flavor, especially in the identifiability story, that many results in this field are proven model by model. We don't really see a general picture here in how the proofs and the results, how they are carried over. I mean, at this point, I'm not even sure what is a neural network. And as you know, can you even give me a definition of a neural network that encompasses both classical neural networks, CNNs, but especially attention mechanisms, where a neuron should correspond to an attention head? Can you even tell me what is a neural network with a definition that encompasses these two things? I don't know. Even in the algebraic context, I really don't know anymore what a neural network is, and the proofs are done case by case. And the second thing is, of course, the elephant in the room. Okay, all this is nice theory. It's mostly a descriptive theory. We try to explain what we see and what especially the empirical community sees in the many phenomena that are being observed. But of course, the desire would be the, something you would want is a prescriptive theory, something that tells you how to design models or how to train them, a prescriptive set of principles that come from this. Is it possible with this? I'm not sure. I'm not sure. It's very hard for a theory to be prescriptive, right? In general, we've seen it in deep learning many times, but I don't know. Maybe once you understand this invariance, dimension, degree, and how singularities work, maybe you can design a model that has a prescribed geometry of singularities or a prescribed curvature degree. We are not at that level at all yet. And so with that, I thank you so much, and that's the end. Thank you.